In this video, I'm going to chat about actually calculating what your position tolerance should be. So I've got an assembly on the board here. It's just a little micrometer holder. We use it for training purposes, but it's got all kind of dimensions and tolerances, and I can really explain how you apply GD&T to an assembly, because GD&T is really for assemblies. You know, you can apply it to detail parts, but you don't really get what it does until you start doing tolerance stack-ups and seeing how it all works at the assembly level. So let's dive right in. This is the part we're going to be looking at. So it's just a little micrometer holder. So you'd put a micrometer here, you got a little couple of screws. What we're going to be looking at are these two socket head cap screws here that go through this piece and into this little base plate. So I'll show you another view here. So we've got the two socket head cap screws. They're going to thread in to this base plate. They go through this piece. So let's move to the detail drawings of each. This is our base plate. The way I've dimensioned this, because all it does is, you know, hold the thing steady on a table or whatnot. We've got datum A, which is this flat plane. It's going to mate to the next piece, so datum to datum contact. The two threaded holes that the socket head cap screws go through are considered a datum. It's a pattern feature that becomes a datum. All of the dimensions for the outside of the part come from those two holes. The reason I've done this is because the holes are the functional portion of the part. Everything out here can mate to air, so we don't necessarily need that to be a datum feature. The datum feature are these two holes, this plane right here, everything else comes off of it. We're going to have a position tolerance, so we're going to calculate in a minute for those two holes. And then we've got our datum feature symbol indicating that those two holes make the pattern. So the size of the holes are 1/4 There's two threaded holes. We'll have a projected tolerance, and I'll show you how to calculate that as well, so that we don't have to calculate the tilt when it goes through the next part. So the part that gets mated up, you can see here are our counter bores. Our counter bores for our clearance holes, right? And then this extra area right here is our clearance hole. They're dimensioned up here from the top. So we got our one basic dimension. And then the same idea with this part. The datum are those two holes. You get less stack up when you do it this way because the holes and the planes, so this datum A is mating up to datum A of the part, the base plate we were just talking about. The two holes in each of the two parts line up, they're both datum, so you don't get any stack up between all of this stuff. Now, the size right here, the 2 times 0.290 plus 14 minus 9, that just comes from a chart. So you pick a size or two up from your fastener size, and then you go from there. Now, we're going to apply the MMC symbol because they're clearance holes. There's no requirement for this to locate anything else, so we don't care if the holes are too big, as long as, and this is something you can do in stack up, as long as you have enough bearing surface for your socket head cap screw. That could be an issue if you let this hole, the clearance hole, become too large. You might have no bearing area for your socket head cap screw, and the part could just, you know, come apart. We don't want that. So we're just going to look at our clearance hole right here. The counter bore we're not going to worry about. Typically, you want, if you have two diameters mating to two diameters, only one set needs to locate. The other one can be as big as it needs to be. In this case, the counter bore, there's no real size limitation on it. It could be huge, right? It's not doing anything other than providing clearance. The clearance hole, on the other hand, can't get too big because of the bearing area we just mentioned, right? So we're going to apply our position tolerance here, MMC. Now let me show you the equation we're going to use, and I'll write it up here. So the equation for fixed fasteners, when one of the fasteners is fixed by threads or welding or however, in a way it can't move around. Right? The equation is going to be tolerance equals hole fastener over 2. So the total tolerance, so we're going to split between the two holes, equals the MMC of the hole, which we'll calculate in a second, the MMC of the fastener, which is usually just the thread size if it's a threaded fastener, over 2. Because one of the fasteners is fixed, we cut the tolerance in half. If they were both clearance holes, it would just be T equals H minus F. Now, if this looks familiar, it's because it's a similar formula to finding clearance, right? If the hole is larger than the fastener, you get a positive number here. If the hole is smaller than the fastener, you get a negative number. Positive number is clearance, negative number is interference. In this case, we gotta have clearance or else the part's not gonna go together. So let's find our variables here. The MMC of the hole is 0.290 minus 0.009. That's the smallest within the limits of size the hole can be. And then the fastener is just going to be our thread size, 1/4 inch, 0.250. Okay, so we'll subtract these out. The tolerance is 31 thousandths over 2. Now, we're going to have to split the tolerance between the threaded hole and the clearance hole. What you normally do here is about a 60-40 split. You usually want to give more tolerance to the threaded hole because it's the more difficult one for manufacturing to get correct. The clearance hole is easier for manufacturing to produce, so you'll give that one less tolerance if you have the option. So split it up however you want. I'm going to do 20 thousandths and 11 thousandths. So I'm not going to divide if you divide the 31 thousandths by 2, you might get 4 decimal places. We don't want that. So you just split it up however you need to. So now we've got 20 thousandths and 11 thousandths. So the clearance holes, or the value in the feature control frame, is going to be a diameter 0.011 at MMC. Good to go. And then the value for these threaded fasteners is 20 thousandths. And then the projected tolerance zone is the thickest the mating part can be. So the way I'd figure that, there's 2 ways to do it. You could say, okay, we're going to take into account the whole thickness of this, about 1/2 inch. But if your counter bore is large enough, then that's not going to come into play. I would say you only really need to take into account this distance right here, which is going to end up just being 1/4 inch plus or minus 20 thousandths. So your projected tolerance zone is going to be 0.27, basically the largest this thickness can be. Okay, and then you could look at that at your tolerance stack up as well and see if you got enough room with that counter bore. You might have to take into account this whole area. The longer the projected tolerance zone is, the more difficult it is to manufacture and inspect. 1/4 inch is a good distance. The little thread plug gauges that are commonly available usually aren't that long, so 1/4 inch is easy enough for manufacturing and inspection to deal with. So that's it for this video. Quick talk about calculating tolerances for position with the fixed fastener formula. If you enjoyed the video, please like and subscribe. Check out the channel for more videos coming soon.